Hello friends, and welcome back to Webronaq. In this video, let's talk about something that quietly makes your computer feel fast, the cache. Here's the problem we're solving. Your CPU is incredibly fast. We're talking billions of operations per second. But the RAM, where your data actually lives, is much slower in comparison. So every time the CPU needs something from RAM, it has to wait. And waiting for a CPU is wasted time. So engineers asked a simple question. What if the CPU had a small notepad right next to it, where it could keep the stuff it uses most often? That notepad is exactly what we call cache. Let's break it down. So what exactly is cache? Cache is a small, super fast memory built right into the CPU itself. Think of it like a notepad sitting on your desk. When you're working, you don't keep running to the storage room every 5 minutes to grab a file. You jot down the things you'll need again on your notepad, right next to you. That's exactly what cache does for the CPU. When the CPU reads something from RAM, it keeps a copy in the cache. So next time it needs that same piece of data, it doesn't go all the way to RAM, it just grabs it from the notepad instantly. Now, here's the catch. Cache is small, really small. We're talking kilobytes to a few megabytes, while your RAM is in gigabytes. So the CPU has to be smart about what it keeps on the notepad. And to manage that, cache itself is split into layers. Let's look at those next. All right, here's where it gets interesting. Cache isn't just one block. It's actually organized into levels, usually called L1, L2, and L3. L1 is the smallest and the fastest. It sits closest to the CPU core, and we're talking maybe 64 kilobytes per core. The CPU checks here first, every single time. If what it needs isn't in L1, it checks L2. L2 is bigger, usually a few hundred kilobytes, but slightly slower. Still way faster than RAM, though. Then there's L3. L3 is the largest cache, often shared across all the CPU cores, and can be several megabytes. It's the slowest of the three, but compared to RAM, it's still lightning fast. Think of it like your workspace. L1 is the sticky note on your monitor. L2 is the open notepad on your desk. L3 is the drawer right under your desk. And RAM? RAM is the storage room down the hallway. The CPU always tries the closest option first, and only walks further when it has to. So what happens when the data is found versus when it isn't? That's the moment that decides your program's speed. Now look at this. Every time the CPU needs data, one of two things happens. And this is where all the magic, or all the pain, comes from. If the data is already sitting in the cache, that's called a cache hit. The CPU grabs it instantly and keeps working. No waiting, no detour. This is the happy path. But if the data isn't in the cache, that's a cache miss. Now the CPU has to go all the way to RAM, fetch the data, bring it back, store a copy in the cache, and only then continue. That round trip can take 100 times longer than a cache hit. 100 times. And this is why cache matters so much. A program that's cache-friendly, meaning it accesses data in patterns the cache can predict, can run dramatically faster than the same program written carelessly. Same logic, same output. But one finishes in a second and the other takes a minute. Pretty wild, right? Now, let's see where this is actually happening in the apps you use every day. Here's the part most people don't realize. Cache isn't some abstract CPU thing. It's the reason the apps on your machine feel snappy. Open a big spreadsheet in Excel and start scrolling. The cells you just looked at are sitting in cache, so when you scroll back up, they appear instantly. No reload, no lag. Reopen a tab in Chrome that you closed a minute ago. The page elements the browser was working with are still warm in cache, so the page snaps back faster than the first time you loaded it. Play a game and walk through the same area twice. The textures and models for that area are cached, so the second pass is smoother than the first. Apply the same filter twice in Photoshop. The second time feels noticeably faster because the data the filter needs is already sitting close to the CPU. Same pattern everywhere. The CPU keeps recently used stuff close by, and the apps you love feel instant because of it. You've been benefiting from cache every single day without knowing it. All right, Let's quickly recap what we covered. Cache is the CPU's personal notepad. Small, super fast, and built right into the chip. It exists because RAM is too slow to keep up with how fast the CPU works. The cache is split into levels, L1, L2, and L3, each one a little bigger but a little slower than the one before. The CPU always checks the closest one first. And every memory access ends in either a cache hit, where the data's right there and the CPU flies through, or a cache miss, where it has to take the long detour to RAM. Hits make your programs feel instant. Misses are where speed quietly dies. So the next time an app feels lightning fast, you'll know there's a tiny notepad doing the heavy lifting behind the scenes. If this video helped you understand cache, hit that like button and subscribe to Webronaq for more videos that break down how computers actually work. See you in the next one.